I advertised, a more specialized talk, but listening to Eve Ostreicher, I understood that it's the second turbulence event in KITP for me, and it's probably the last KITP, turbulence KITP event, if it goes once in 20 years. So, therefore, I will start with more philosophical statements and discussion about the turbulence. And I will provide the personal outlook. And I would like, first of all, tell you that you should fasten your seatbelts. On the progress since the previous KITP meeting. So this is the picture even earlier than the last KITP meeting. It was done by Leonardo da Vinci. And what you see here, this is turbulence. And you see chaos, first of all. But you see order. So turbulence is a chaotic order. And then we can choose what we want to study, what we want to focus on chaos or on this statistical order. And for example, if we are talking about formation of molecular clouds, we are dealing with chaos. It's formation, distribution of supernovae and mass. And this is this part of the spectrum. This is injection. And if you have different supernovas, different other sources of energy injection, you will have here pretty messy structure. And then you will have this universal part. And universal part would be responsible for small-scale fluctuation, reconnection diffusion, interaction of cosmic rays, and it can be described statistically. So we had a discussion yesterday with Norm Murray, and Norm correctly pointed to me that this may not be universal. That can be true, but I believe that Kolmogorov scaling is more universal than the time-dependent distribution of supernova in the galaxy, for example. In any case, what I call turbulence is this part of the spectrum, and I am going to talk about that. Spectrum, yeah, we see. This is famous Armstrong Racket plot with Alexei Chepurnov. We added this part, but there is always a question: what it is? Is it turbulence or geography? It's not my term, but Spangler's term. Why? Because maybe you have go to the beach and you see this grains of sand, also power law. Therefore, these results, which were obtained recently by Cahor et al., are very important, because using this advanced techniques based on understanding of turbulence, it was possible, and actually Dmitry here, who contributed to these techniques, possible to show that it's velocity, it's real turbulence, and it covers 6 orders of magnitude. And here probably we have 2D turbulence, inverse cascade, but they get very well. And we have the same spectrum irrespectively. Here we are going to high densities, but spectrum is the same. So we are in the situation that we have an ecosystem turbulent ecosystem, and molecular clouds, all these structures are parts of this ecosystem. Okay, so I will be mentioning several selected advances in understanding of turbulence since the last KITP event. In the previous KITP event, I would say that turbulence was looked more like a mess. And there were all these modes interacting strongly. How can you do any analytics? It's only numerical work. But now we have understanding of the basic facts of incompressible turbulence. And in fact, the work that Heilo just presented us was a further understanding of this. And it was possible to extend this theoretically to imbalanced turbulence, collisionless turbulence, relativistic turbulence. So it's a big progress, I would say. It was also on the basis of the understanding of analytical properties of turbulence, it was possible to establish some new effects. And the most dramatic is the gross violation of the basis of MHD theory, is gross violation of the flux freezing in turbulent media, and where you can see non-turbulent media in astrophysics. And it introduces some thing that Beche mentioned, a connection diffusion, for example. And on the basis of this theoretical description, it was possible to get some understanding better of cosmic thermal conduction, cosmic ray transport acceleration, and other processes. So, okay, it shows, okay, now it works. And some of this, the developments are summarized by the book that Andrei Berezняk and me published in 2019. Published facts now. I would like to attract this fact, which unfortunately is not well advertised. There were a lot of discussion. What is this slope of the turbulence? And there were a number of papers which were saying 3/2, 5/3. But there is something very, very fundamental. This is prediction of the Goldreich straight line isotropy. And Goldreich theory, which was a computing theory, predicts something different. This is what Goldreich predicts, this is what Goldreich straight line, and these are different numerical simulations. I think it is quite compelling that Goldreich straight line is working. But at the same time, do we know everything? No, we don't know everything. And there was this new development related to my student, Kavli, who is here. And this is related to the driving, dependence on driving, because usually incompressible turbulence is driven by Alsace variables, so magnetic driving, we would say. And this is what is well known. We have this same scales, or scaling for velocities and magnetic field fluctuations. But what's happening now if we have velocity driving, which is probably more relevant to what we have in the astrophysical media? We have a very different driving with more energy in velocity fluctuations and a very different spectrum for sub-Alfvénic driving. So it's when you're driving at velocities less than, Alfvén Mach number is less than 1. So, and when you go to the trans-Alfvénic, you get it back. Just another illustration of this. a ratio of alpha to slow mode energies. We find that in the velocity driving, alpha modes are subdominant compared to the slow modes. Well, let me talk about the second part, which is actually my talk. Right, I will be trying to show you some broad view picture of what's happening when we have cosmic ray interaction with turbulence. And I would like to mention something which I learned from a great physicist who passed away last year, Frank Shu. And Frank Shu was saying, what is the ratio, what is the relation between the simulations and theory? And he was giving an example. Imagine that we have a super computer which can present us with an exact picture of the Crab Nebula. All processes Crab Nebula we see. Do we understand how Crab Nebula is working? His answer was no. We need to take a pen, a piece of paper, and try to understand what physics is there. And at the same time, another great mind, Randy Jacobi, was pointing out that there was a well-established work on cosmic rays, theoretical, but then simulations did not correspond to anything expected from the theory. So I would vote for the combination, synergy of theory and numerics. And there are good reasons why theory may be wrong and why numerics will be wrong if we do not combine them. So let's discuss what's happening with the cosmic ray transport. We know that there was this phenomenological model of 2D and slab, but it was never observed in numerical simulations. And what was observed in numerical simulations, and this work with Jungi and Cho, was that we can decompose into 3 modes, and they have different anisotropies. Slow and fast modes are anisotropic, therefore they are not efficient. And this became, after that, fast modes became very popular in the scattering of cosmic rays. So with Gianfranco Brunetti, we explored different ways of accelerating cosmic rays in clusters of galaxies, and there were different ideas that we considered, and one of them was acceleration of the fast modes. Then we were considering also a connection and other processes. This is from the well-known review from Brunetti-Jones, which summarizes this theoretical advances. For example, it shows more extended, due to effective collisionality, range of turbulence, and shows more efficient acceleration. But let's put it this way. Do we understand everything? No. And today we had a very nice talk about the curvature acceleration. But I will want to discuss some other effect which is also present. And this is related to a well-known effect, mirrors. Magnetic mirrors were discussed by Karlsruhe in many papers, and what we have? We have a particle, it conserves its second type diabatic invariant, and it's gyrating, and it's reflected from the regions of higher magnetic field strength. It's a very well-known effect, and why wasn't it considered in terms of acceleration? It was not considered acceleration because particles go back and forth, and it's not accelerated, it's evolving together with the evolution of turbulence. But is it true if we consider realistic turbulence? It's not. Why? Because we have super diffusion of magnetic field lines, and this gentleman is here. With him, we quantified this super diffusion. It's for as we move along magnetic field lines, the differences between magnetic separation goes now not as S in diffusive, but S cube. And this was confirmed by Andre. This was confirmed also by Xiao. So what does it mean? It means that we must combine these mirrors with the effects of superdiffusion. And what it means? In the classical picture, the Carlsrud was considering, if you are trapped, you're trapped. You are just going back, forth, and you are not getting energy. But here, what's happening? Because it's not possible to retrace yourself. You are interacting with one mirror, and then you are not going back to the same mirror. You are going to another mirror. And this is, results in the mirror diffusion, a new process that we introduced. And let's see, hopefully it will not be so eventful. Yeah, this is the Xiao with her student is done this simulation. This is magnetic and this is what are the trajectories. You are moving not from one mirror to another and trapped, but you are diffusing. Oh, I think again it will. I'm sorry for this glitch. Okay, and what does it mean? Mirror diffusion is very slow diffusion. And as a result, we are getting to the situation that we have Levy flights. We have a random walk agents of slow mirror diffusion, and then your pitch angles change. And you are getting to a new regime. And this is also was confirmed in the simulation by Xiao and her student. You have here slow regions, slow diffusion, and then the Levy flights. In terms of the acceleration, and I will be very fast, just mentioning a couple of facts. It's very simple, you know, this electric field. If you have compressions by slow wormholes, you will be accelerating your particles. Well, what is happening? When you have, we are considering incompressible stimulations and the incompressible situation, and in this case, you compress in one direction and you extend in another direction. And if you do simple yes, proportional to the momentum of the particle, so it's good. But there is this factor, 1 minus 3 mu squared. And if you have scattering, mu squared average 1/3 is 0. And what does it mean? It means that you have no acceleration if you are changing mu. But the fun thing about this mirror acceleration, it does not change mu. So you have a subset of particles with small mu, which is getting acceleration. And therefore, Again, I will not go into details how these equations are obtained, but I will attract your attention to this expression in comparison with the traditional fast mode acceleration. It has, here we have a small factor, velocity of sound over c, and here we don't have. So we can have a much more efficient acceleration. So this is my summary. And well, the most important is astrophysical turbulence is not a mess. And if you want to describe the cosmic rays physics, you should understand turbulence. We are not yet at the final stop with this too, but we are going there. And understanding of cosmic rays and acceleration in galaxy clusters requires input from these 2 points. Thank you.
Questions for Alex?
Questions. You mentioned that there's no retracing of cosmic rays in the mirror. So do you mean there should be enough scattering? What if the mean free path is very large?
Well, it depends on your mu, because there's your mu is yeah, it depends on this delta B. So, and you have the whole, range of the fluctuations of magnetic field. There's a compressible magnetic field fluctuations in incompressible media. And if your mu is small, your particle will interact with the minute fluctuations of magnetic field, which are pretty frequent. But if your mu is becoming larger, you are interacting only with the largest magnetic field fluctuations. And this increases your actually mean free path.
I have one myself. And will the mechanism of mirror acceleration work at any energy, or do you expect to have particles that have thermal energy, essentially to have some other mechanism that, for example, inject the particles to higher energy, or will it work already at the thermal energy?
Well, mirror processes are applicable to every energy. So what we are just discussing that we are introducing some new thing, which is mu dependence of this. But we will have applicability to all energy.
But you have not checked against simulations?
As I showed, the simulations were working with with their limitations.
Yes.
It's the work in progress. I don't expect anything that would be happening with that.
Okay, thanks. Bete?
Sasha, when we test mu, the critical mu, under this condition, the theory, both theory and numerical simulations, you have to filter the background plasma so that you only look into the scattering or the mirroring of the particles, right? However, when we have everything together, we may have, particles trapped in current reconnection layers, and they get accelerated too fast stochastically, so that they may lose all this information on the transport and the effects of the mirroring. How can we put both effects together I mean, I think it's a kind of, you know, it depends on the time scales that we are talking about, right? Comparing the time scales.
Definitely. If the previous question, then you should also consider the evolution of the turbulence. These simulations that I will be showing do not involve evolution of turbulence.
Exactly.
This is only the propagation. We need to have as much computational power as, for example, who has to have many slices and then play with this. It has not been done yet.
Okay.
Okay, we can discuss this.
Yeah, Alex, I was hoping you could say a bit more about this big power law that you showed. So there was some work by Kahu, I think, and also the earlier work. I have to admit, I never understood the early Armstrong work, or what's exactly plotted there. Is it really velocity on the y-axis?
I think you're asking about this, right? Yeah. This is well known up to here. This is 95 famous work by Armstrong, Rickert, and Spangler. This part we added using WAM data. These are all electron density fluctuations. And you know, Irina told us that electron density fluctuations can reflect velocity. Some people believe, some people do not believe. So it's good that we have it, but it's much better to have directly. And Irina probably will agree with this. So if you have spectroscopic data, it's this is a with spectroscopic information. This is H1, this is CO, and they this is in direction for Taurus cloud. And they fit for many orders of magnitude nice Kolmogorov law. This is and this is only possible because we filter out parasitic contributions from compressible density. And we don't use centroids. So you use centroids, you will not get it.
Okay. If there are no other questions, let's take Alec again. One more question. We have time. We have 2 minutes.
Just to be very clear there, Alex, so what you're plotting on that plot is the power spectrum of intensity structure.
No.
Okay, then what is it?
No, it's not intensity structure. It's the power law of fluctuations of velocity, which we infer from the analysis of fluctuations in the spectral lines. You are smiling, I know, but it's been unlike your...
It's just not velocity.
No. It's what I'm just saying is this has been tested with 2 fluid simulations. It's not what is written in your paper in 2019 where you questioned this.
I think the question, Alex, was just what is plotted.
Well, yeah, what is the measurement that's plotted?
It would be nice to know what the measurement actually is.
This is, you know, you measure fluctuations in channel maps. And these fluctuations in channel maps are affected both by density and by velocity. And with this gentleman, Dmitry Pogostian, we developed a theory which shows how to distinguish the two. And that's what, yeah.
Okay, let's thank Alex.